Alright, so today we are going to start with the last topic. Now, remember what happened in the LSTM encoder decoder architecture? What happened in the LSTM encoder decoder architecture? So, this was your decoder, this was the encoder, there was just too much reliance on this particular network, this particular vector. We of course have these recurrence relations, and so one thing is LSTMs or recurrent neural networks, they are inherently sequential. Write that down. Okay. So, this is inherently sequential. Given one example, I can choose any example, but given one example, all the elements of that example are actually timestamps, right. This will happen first, then this will happen next, then next. So, that limits the way you can process the example. Okay. One thing. Second, so inherently sequential and too much weight on this. Which problem did we solve using attentions? Too much weightage on this particular vector. So, how did we solve that? We said here you have S vectors, here you have H vectors, they both are what? They both are simply AT, the way we are using them before. Now what happens? We say when you want to output y hat here, don't just depend on S1. Don't just depend on S1, take help of encoder. And how are you going to do that? This S1, you take dot product with all three of them, right? You will have this particular vector, then what do? Once you have this dot products, you have this vector, नाम क्या दिया था यार इसका? S1 H1, S1 H2, S1 H3, and then this was called alpha, and this is actually alpha 1, right. Now what did we do next? Is this sufficient? Now you took softmax, right? We call that A. So A1 would be softmax of alpha 1. And then what did we do next? We said that the values will be what? A1 times H1 plus A2 times H2 and all that. Actually in this case just A3 times H3. What is A1, A2, A3? A1, A2, A3, what are they? A1, A2, A3 are actually probabilities, right? So, sorry, A11, okay, thank you, right, okay. These equations are fine. Now, in this case, what kind of different vectors do you have? You have vector H of the same size as S. So, you have vector H coming from encoder, you have vector S coming from decoder, but they both have the same nature in the sense that they are hidden units in a RNN, right? These ones are in decoder and these ones are in, sorry, These ones are in encoder and these are in decoder, right. When giving output y hat here S1, you take this thing. Now what is V? What is value? Actually this will be a value at 1. What will that be? Look at this equation. This is a linear combination of what? This is a linear combination of hidden values or hidden, what do we call them? No, not parameters. Whatever, okay? Hidden vector. यार क्या बोलते हो उनको? Hidden नहीं बोलते हो? What? Whatever, right? So H1 corresponds to the first timestamp, H2 corresponds to the second timestamp, and so on. What is A11? This comes from here, this comes from here. A11 gives you, are all AIs strictly greater than or equal to 0 and lesser than or equal to 1? There is one more property, summation AI is equal to 1 for this whole thing, okay. So these AIs, they will sum to 1. So what does this mean? If AI is, let's say, if AI1 is, let's say, 0.8, what does it mean? My value will be 0.8 times H1, let's say 0.1 times H2, and let's say 0.1 times H3. I have a value which is a function of the hidden units of the encoder, and then what do? Just take a linear combination, you get this final vector, okay. Now what do? What do we do finally now? How do I compute the output? ऐसे मत करो यार, मेरे को भी नहीं याद है. Yes. How will you compute y hat? See, you have done all these things here. You have got this vector V1. Attention is done. Take V1, take S1, compute y hat, right. So y hat, if you see, was a function of just S1 until now, but now it becomes a function of, right. So you just concatenate, V1. What will be the dimensions of V1? What will be the dimensions of V1? Same as H and S, right, because if you see, V is nothing but a linear combination of H's. H's are nothing but they are being taken dot product with S's, so they all have to have the same dimensions, okay. So how many different kind of vectors we are dealing with? 3, H, S and V, okay. Now, so this is just the recap of attention. Tell me, what will, does bringing attention change my number of parameters in the model? How many parameters does attention layer have? This equation, 0 parameters. This equation, 0 parameters. This equation, 0 parameters. No parameters added? Yes or no? It does. Where? If you see your earlier you were just function of S1, now you are function of this comma this. So this neural network, these two neural networks are actually different, right. So there you make a change, else there is no change. And of course you can always bring in parameters, but I am not doing that here. So you can do, you know, S1 times some parameter matrix H1 if S and H are of different dimensions, or even if they are of same dimensions, you can still have a square matrix, as we will see they have it in transformers. Okay. So with this, my main source for these next 4 lectures will be the blog post, The Illustrated Transformer by JLMR. So I will write it here. Okay. This is our main source for this. Now, so if now attention is all you need, and of course attention is all you need, these are two my references. Now see, what does attention is all you need, right? This paper was written for which problem? Translation. So they wanted to translate French to English, German to English, and so on. Okay. So attention is all you need was specifically written for translation. Now if you have translation, what will it be? So let us say this is your transformer. What will you input? So input was and this came out as now. So we will keep on zooming inside here. Now how should we go in? So I will just redraw all the figures that are there in the blog, and maybe you should as well. Okay. So this transformer now becomes, so you will have encoder, decoder. So again this goes in here, and what comes out is this. Okay. Now let us look at what is there inside every encoder. So now we try to, so every encoder is nothing but just stacks of 6 encoders. So let me just do that. And then you have this 6 times. So right, you have this thing 6 times. I am overloading the name encoder because we are calling this block of 6 encoders also encoder, and similarly for the decoder. Okay. And what important you have here is, so these things are, this is my transformer, these guys will give so this is how your transformer looks like. How many encoders here? 6. How many decoders here? 6. And right now we are talking about which paper? Attention is all you need. Okay. So this is what we have. Note one special thing. How are encoder and decoder connected? Which thing connects them? These output from 6th encoder in this case, right? So I'll specifically mention these numbers. Encoder, the 6th one, the output of that actually goes to every decoder, right? So output of this whole encoder block combined is fed to every decoder, be it the first. So all these vectors, they are basically giving me the same numbers, right? It's not that different numbers are sent here and so on. These are the output of this whole block and is fed to every decoder. Okay? Sure. What happens next? What do we need to do? Now since we are drawing it in this fashion, this is where your inputs will be taken. Okay, and outputs will be up there, because so this is the flow. And here you will have okay. Any questions until now? How many of you have used transformers in your projects? Right. Okay. So let us continue with this. Sorry? Okay. So what do we do now? Let's talk about every encoder block now. So every encoder block looks like, which every encoder block? These guys, right? So this one of the 6, it looks like the following. So here you have 2 layers, right? The first one is self attention, and this one is feed forward neural network. Right? From now on, I will be writing this as FF, NN and self attention. So total how many things can you see here? This is one encoder block. How many such are there in this paper? 6 of them stacked over each other. These guys will take input and pass output. Okay? So you have outputs here. Next, what do we do? How does at the same time decoder look like? So decoder basically, so what will happen? You take input here, how many times this, so this is kind of a loop. These guys are input for whom? So this is my input, right? And these are the output of encoder 1. What shall I write? Fed to encoder 2 or input to encoder 2? Input to encoder 2, right? What will happen next? The output of E2 will serve as input for E3. What about output of E6? Output of E6 will be sent to decoders, all the decoders. Okay. So how does decoder look like? Decoder looks something like this. Just one decoder block now, not. So this here you have self attention, then you have encoder decoder attention, and then again you have feed forward neural network. What is missing? So there will be things coming from this side, and where is that? So tell me which block takes care of in output of E6 that is fed as input to decoders. So this was my encoder, this is my decoder. This encoder decoder attention, वहाँ से वो जो चीजें आ रही हैं, they are being fed here. Okay, don't worry too much about this. We'll make this structure much more concrete. Now, so we again focus on this now. Tell me what happens here at the input. Those who have done transformers before are welcome to help me out. Yes. So we are fixing here now, how does each input look like? And I'll stick to the numbers used in attention is all you need. Okay. So how many total inputs here? Attention is all you need fixes this to, I think, 512. So each input here is a 512 dimensional vector. How many such inputs? So if I remember it right again, you guys keep on confirming this. Total number of inputs was 512. No, is this 512? Oh, yeah, this attention is all you need is 512 here, 512 here. Just make sure it is so. Okay, even if it is not so, it does not matter. So how many inputs total? 512. Each input is how many dimensional? 512 dimensional. Okay. What happens here? See, this is taking us to self attention now. So what happens here? Input is okay with everyone. How many total input? So if you remember, compare this with LSTM encoder. How many inputs were there? See, here you are taking all these 512 inputs in parallel. What happened in LSTM? First one, compute the hidden state, then using that hidden state and the next input, compute the next hidden state. So my hidden state at timestamp t depends on input at time t, which is xt, and also hidden timestamp at time t minus 1. So it depends on ht minus 1 and xt. Okay. In this case, you feed all of it parallelly. What happens here now? So let's try to understand what is self-attention. What is self-attention? Maybe I'll do it here. Yes. Anyone? And in fact, but I'll do that once we are done with the self-attention. So let me write this particular equation for you. And which is actually, so let me just write it here again. So they are the same things, you just have to, we are just drawing them. So, and this figure is from the paper. So let us just understand this one, right? What are these operations? What are QKV? Don't ask me right now, I will tell that to you, but whatever QKV are, what happens next? Matrix multiplication, right? So you somehow multiply this Q, then you scale, mask is optional, so I will keep it optional for the time being. Then you take softmax, then you take matrix multiplication again, right? So this is just a pictorial representation of this equation here, maybe have a look at it. Let's go top down. Forget this one. Softmax you are taking of something, softmax you are taking of this thing, right? What is this matmul doing? Matrix multiplication. Softmax of this whole thing doing it with V. Okay. What is QKT? QKT is your here. What is T there? Transpose. What is scale? Dividing by under root of some number dk that we will see. And mask is optional. In this case, we don't have it right now, right? So, we are not keeping mask for the time being. Done? Tell me what is happening here. Yes. You have to help me out. I can't do this alone. Yes. What is the operation going on here? What are Q, K, V and so on? Compare it with LSTM. See, in LSTM we had 3 vectors. What were they? I mean, in the attention with LSTM we had 3 vectors. What were they? H, S and V. What were they actually? H was H in the encoder, S was S in the decoder. So, what is the role of S here? The role of S as they claim in this paper is that it is a query. Why do they call it a query? They try to compare it with databases. I mean, I don't see in this paper they say that profoundly, but later people have tried to decode it in terms of databases and so on. I don't think I'll do that. So, this is query. This is what? What was K? So, this is your key. And what are V? V are values that are same as Q, K, V. So, these are values. Remember those equations for taking attention? What were the equations earlier one? Take dot product of H and S. So, what does this operation look like? This is nothing but H and S, right? Now, we are calling them different. They are not H and S anymore, they are Q and K. What is V? So, if you remember, this operation is same as before. एक बार ये forget this scaling factor. You computed dot products and then you took softmax and then you multiplied this with V. Exact same operations are happening. So, don't get intimidated by these equations. They are same as what we have done before. Okay. Any questions here? So, this is query because what happens in LSTM when you are trying to output at a particular timestamp? S1 goes and queries all the H's, which one should I depend most on when I want to output at this particular timestamp, right? Which value of H should I depend the most on, and it will give me a probability distribution, and then my V's will be just a function of those H's. Here if you see, there is a difference. What is V? V is a third vector here. There V was even though a third vector, but was a function of H's, right? It was a function of H's depending on linear combination of, so it was a linear combination of H's, right, where weights were A's and A's were functions of S and H. So, there we had just 2 vectors mainly, S and H. Here you have 3 distinct vectors. what this paper comes and says is, see, in earlier version of attention, you are actually doing 3 operations that you could do on 3 different vectors, but you are doing it only on 2. So we try to segregate them as much as we can. Q, K, V. We needed 3 different vectors, we have them. Now, how should I make this neural network that does this whole thing? How do I go and zoom inside these operations now? Given that every Q is, so assume every Q is, so let's say my Q, K, V, everybody is a 64 cross 1 vector. Okay. So all these guys are 64 cross 1 vector. What do I do now? What is this operation telling me? What should be Q? So now we have to relate it with what we had drawn there. Okay. Now, if you see here, so let's say, so let me keep this for some time later. And now what we have is inputs, decoder, output. So let me just make these 2. This is my 1 encoder, this is my right. And this was of course self attention. X1 is, what are the dimensions of X1? 5 and 2. X2, 5 and 2. Everybody is 5 and 2 dimensional, goes input here. And then what is output here? See, there is something called D model that they don't define in this paper, I think, but is defined in the later GPT ones. So I'll use that from here only. D model equal to 5 and 2. 5 and 2 means how many inputs am I taking? So how many inputs am I taking? 5 and 2, but for the illustration we are drawing just 2. Every vector is 5 and 2 dimensional. There are 2 different 5 and 2 things. What are they? Total you have from x1 to x of 5 and 2, and every xi is 5 and 2 dimensional. Output of self attention layer will be, what will be the dimensions? D model says this should be 5 and 2. Right? What do we call it? Let's call it Z1. So if we call it Z1, this will be 5 and 2 dimensional. Z2, this will be 5 and 2 dimensional. This is now fed to the feed forward neural network. This is the easy part. How does every FFNN look like? Every FFNN, right? So every FFNN simply looks like, how many numbers is it taking as input? 5 and 2. And then it basically upscales to a 4 into 5 and 2, that is 2048. and then downscale it or project it to again 512. This is what every FFNN looks like. So now we are just looking at one part, because these guys are parallel. You can input this x1 and x2 input at the same time. They will be processed together on GPUs in parallel. Every branch is, so in the original transformer, how many branches will you have in parallel? 512 branches being processed in parallel. This direction is sequential, right? Once you take this branch, this direction is sequential. But what is parallel here is every x1 is processed independent of, so every xi is processed independent of any other xj, right? So you have some kind of parallelism. So you have these 512 parallel lines going up. We'll decode this. What does each FFNN do? How many total parameters here? 2048 into 512 plus 2048 and then 512 into 2048 plus 512. So this is as simple as this. We are done with this. We are now supposed to take care of self attention. हाँ
सर जो ऊपर इक्वेशन लिखी थी उसमें सॉफ्टमैक्स दिया था क्यू के ट्रांसपोज का.
यस.
तो सर जो क्यू के ट्रांसफर है वो तो एक तरीके से 64 पर 64 का वेक्टर हो गया.
आई एम नॉट येट डन विद दिस, राइट? देयर विल बी अ होल लेक्चर ऑन दिस. So I just wanted to say here that this is same as what we have done before. There we had two vectors. So this equation, how was it before? You had S, or if you took, let's say, so query is your S H transpose, you get that S1 H1 S2 S1 H2 vector. There you were not dividing by this scaling factor, so this was not there. You took softmax of everything, that gives you a vector of A's, and then you multiply that with H's, right? In this case V's are not H's, in this case V's are V's themselves, a third vector. Okay. Now first question comes, how do we get these vectors, right? How do we get these vectors? So they are a function of input. So how do you get vector q, for example? Right now I am not talking about, let's say, tensor, we are just talking about vector q. How do you get a vector q? There is a matrix q and you multiply that with the input. Okay. So this is how you get query vector. How do you get the key vector? How do you get the value vector? Sorry, this will be small v. Okay. So for every x you will compute QKV. So what will happen? How will I get the first query value, first key value, first V value? Quickly. जल्दी से देखो, because we are done. What I have left for you to answer is, where should I put superscripts or where should I put subscripts? What are these equations giving me? देखो, Q, K, V, what are they? These are my parameter matrices. Okay. What are x's? What are the dimensions of x? 5, 1, 2. Is this the same x? How will you compute? So which x is this? x1, x2, x3 कौन सा x है? Sorry? So that's my question for you, and that's not easy to answer. X is x1, 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 that will give you q1, k1, v1. Okay. How many times will I do this? 5, 1, 2 times, right? Because for every input I need to convert them into query key and value vectors. What operations do we do on them? I think we'll start that in the next class, but we'll start from here in the next class. But the structure by and far should be clear to you. What should be clear is a transformer in this case will take 5, 1, 2 inputs. Each input will be of size 5, 1, 2, and what is the most important part? They will all be processed in parallel. This was not the case before, right? So branch x1 is independent in itself. Give it to one GPU and it is done. x2, earlier x2 processing dependent on the processing of x1, so you had to wait. And where it is still sequential, in the vertical direction it is still sequential. You can't go to encoder 2 without processing encoder 1, right? Because that serves as input to the encoder. We'll do that. We won't do it 2D, we'll do it vector wise, row wise. Astha, Adhiraj, Akshat, Amit, Arohi, Arukshita, Ashmit, Disha, Divyanshu, Ishan, Garv, Himanshu, Kanishk, Kashish, Keshav, Kushagr, Melissa, Muskan, Nilesh, Niharika, Paras, Payal, Rani, Ridhika, Riya. Ridhika is there? Okay. Riya Singh, Saurabh, Srishti, Shreyansh, Siddhi, Saurabh, Swastik, Vaibhav, Vrinda, Yash, Abhinav, Archita, Nitin. Chalo, done. Thank you.